In the previous video, we discussed a potential complication with regards to identifying the relationships between phases from a subset of isostructural phases. It was mentioned that most isostructural phases aren't concerns in this aspect because they generally originate from a single atom or ion substitution. Sometimes a compound will display the same diffraction pattern for an experiment set out of a wide variety of solvents, but also show a weight loss in the TGA and no water content by Kf. These compounds form solvates in such a way that are non-selective. We call these promiscuous solvates, and they can form for several reasons. First, the solvent may provide an essential interaction required for the crystallization, such as a bridging hydrogen bond interaction. Depending upon the space available in the surrounding environment, this might be provided by any number of solvents. If it requires one donor and one acceptor, it may utilize water, methanol, ethanol, or any other hydroxyl-containing compound. If it requires two electron-paired donors, it may utilize acetone, tetrahydrofuran, dimethyl sulfoxide, or any other solvent containing a carbonyl or an ether. This does require that the sterics and the electronegativity of all the solvents are suitable, which is often not the case. Second, the solvent may have no interactions with the compound at all, and may simply exist to fill a void that would otherwise create a major thermodynamic obstacle to crystallization. In this situation, the most important quality of the solvent is simply that it was present during the process, and is of the appropriate size, and does not actively interfere with the interactions that influence the crystallization. These solvents may exist in isolated voids, like the bubbles and blocks of Swiss cheese, in which case they will generally only be liberated upon melting. Alternatively, they may exist in a channel, like the holes in a sponge. This was briefly alluded to in the TGA discussion. Channel solvates can often be desolvated at ambient temperatures under vacuum, or they may simply do so on their own through entropy. If the desolvated form lacks enough stability, it may collapse into an amorphous powder. If it is strong enough without the solvent, it may persist in a desolvated state, either with transient vapors permeating the channel or by scavenging atmospheric water to fulfill the occupancy of the thermodynamically unstable voids. This last group of compounds is the most important in the pharmaceutical industry, as potentially problematic solvents required for the synthesis route still must be removed before preparing a compound for introduction into a living patient. Most organic solvents utilized for these reactions have extremely low tolerances within drug products for use in the human body, generally in the parts per million range. Chloroform and dichloromethane are excellent examples, as both can form hydrogen bonds, are highly volatile, lending them to the potential to form solvates, which can then be turned over into hydrates or anhydrous forms through various drying strategies.